Good morning, fellow boys, mathematicians. Welcome back to another video. In Papa Flammy's advent calendar, I have derived the rotation matrix just for fun, and equivalently we are going to derive the reflection matrix today just for fun. Most people are probably not familiar with the reflection matrix, so let me explain it first what we mean by the reflection matrix. So let's say we have a coordinate system and we are going to derive it in 2 dimensions once again. And we have a certain vector v, for example, right here. Okay, and our reflection matrix is a tool. For example, if we would span a line right here with a certain angle theta from the x-axis to this line, and this line is going to be our reflection axis, you could say. So we have then a certain angle phi, you could say, between our vector v and this line L right here. And then we are going to reflect our vector v, for example, like this right here, and we are going to get a new vector v prime, for example. And the angle between this line L and this v prime is the same angle as the one between our v and our L. This is what our reflection matrix is going to do. At first I would like to take a look at our vector v, how it's placed in this coordinate system. So we have a vector v right here with a certain length r right here, that's just the magnitude of this vector, and also we have an angle alpha, for example, between the x-axis and our vector v. We can use Papa Pythagoras once again to find out the x and y coordinate of this thing. So this line corresponds to the y length and this line corresponds to the x length, meaning our vector v, without the vector arrow, I'm sorry, that's just some physicist stuff, consists of some x and y coordinate. And well, now we know that our x, if we just solve for x, polar coordinates, is nothing but r times the cosine of alpha. And down here we have r times the sine of alpha. Now we want to take a look at our new vector v prime that we are going to get. So for example, our new vector v prime is going to be up here. It really doesn't quite matter. And it's going to consist of some y prime coordinate and some x prime coordinate. Also we have a big angle in between here. Let's call it gamma, for example. Okay? So that's our angle gamma being enclosed by the x-axis and the v prime vector. If we just reflect this vector, our magnitude really doesn't change. It's just the same magnitude, just with our just like with our reflection matrix. Meaning, once again, we have for v prime that it consists of some x prime and y prime coordinate. Namely, this is r times the cosine of gamma and r times the sine of gamma. Now we have to do some playing around with the angles. That's the only difficult part, you could say. I for myself like to mix up stuff and then I'm not arriving at what I actually want to arrive at, but we are still going to give it a shot. Once again, we have a coordinate system right here. We have a vector v right here with an angle alpha enclosed here between x-axis and our vector. Also we have this line L being spanned out right here, and between our v and this line L we have a certain angle, let's call it phi, just like before. Also, let's say we have our v prime, that's the reflected vector, right on the y-axis, for example, also enclosing this angle phi. Like I said, our reflection matrix is going to tell us exactly where our reflected vector v prime is going to be after we've applied this line right here, having a certain angle between our L line and our x-axis. Let's call this thing right here, I really don't care, theta, for example. Okay, now we can do some trigonometry right here. Some angle playing around, because, you know, this angle right here between our x-axis and our vector v prime is exactly our gamma that we have proposed right here. Okay, so our gamma, what is it going to consist of? Well, it's going to be just phi plus theta right here. Also, what, for example, is our angle theta? Theta is nothing but, well, phi plus alpha. And just like we did with the reflection matrix, we want to kind of substitute our original vector in the end. So our angle gamma that we have to find out has to consist of our reflected angle, you could say, of our line L, and also with regards to our alpha, because we want to substitute this right here in. So why not solve this thing right here for phi, so that we can substitute phi into here, meaning phi is nothing but theta minus alpha. We can substitute this value into here and get that 2 times theta minus alpha is nothing but gamma. Okay, that was actually quite easy. We can plug this into here. This is nothing but r times the cosine of, okay, 2 times theta, the reflection angle, minus alpha, and r times the sine of 2 times theta minus alpha. And just like with our rotation matrix, we can actually use addition formulas right here. We're going to end up with a big S vector right here, r. Okay, now we can just use the addition formula for the cosine, just with a sign switched in the end. So this is the cosine of 2 times theta, just grab your list of addition formulas, times the cosine of negative alpha, but this is just the cosine of alpha, you could say. Okay, and then in the normal case, we would have negative. I'm going to write it out. Then we have the sine of 2 times theta, sine of negative alpha. But the sine of negative alpha is nothing but the negative sine of alpha. So we can bring this to the outside. That's where we get this positive sign from. Okay, now we have r times. Okay, cosine of 2 times theta times the sine of negative alpha. And then we have positive sign right here in the addition formula in the normal case. And then we have the cosine of negative alpha times the sine of 2 times theta. Closing off everything. Cosine of negative alpha, well, it really doesn't quite matter. It's just the cosine of alpha, it's an even function. But we can drag this negative sign, just like before, to the outside. We are going to get, let me sort everything a little bit. At first, we are going to get r times the cosine of alpha times the cosine of 2 times theta plus r times the sine of alpha times the sine of 2 times theta. Down here we are going to get, okay, let me bring this in a different order. I'm going to distribute it into here and then we are going to see what we get. This is nothing but r times the cosine of alpha times the sine of 2 times gamma, negative sine, r times the sine of alpha times the cosine of 2 times theta. Okay, here we go. That's actually quite good because r times the cosine of alpha is nothing but our original x coordinate and r times the sine of alpha is nothing but our original y coordinate. Meaning we are going to get overall that v prime is now nothing but, okay, this is x times the cosine of 2 times theta plus y times the sine of 2 times theta, x times the sine of 2 times theta minus y times the cosine of 2 times theta. And now we are going to let some vector calculus magic happen. Namely, this thing right here is nothing but some matrix, namely cosine of 2 times theta, sine of 2 times theta, sine of 2 times theta, minus cosine of 2 times theta, multiplied by x and y vector. Cool, and that's really quite good because you see this right here is actually our reflection matrix that we wanted to get. So this is nothing but the reflection matrix where we reflect by an angle theta times our, well, v in this case, our original vector. There are many applications of this right here. For example, why not take a look at the complex plane, for example. Let me erase a little bit. So, what's an application? Let's say we have a vector right here in the complex plane, okay, and this vector is, for example, 3 and 1, okay? That's a complex number corresponding to 3 plus I, for example. Now what we want to do, we want to find its complex conjugate, meaning z line, z head, whatsoever, the complex conjugate is nothing but 3 minus I. meaning geometrically seen that we are going to reflect that thing right here on the x-axis. That's our complex conjugate down here. Meaning, if we would interpret our x-axis as our line L, this line L and the x-axis are going to enclose 0 degrees Celsius. So 0 degrees overall. Meaning, our reflection matrix of 0 in this case, okay, we are going to use this, is going to be, okay, cosine of 0 is just 1. That's going to be 0 and this is going to be negative 1. Meaning we have a matrix 1, 0, 0, negative 1. If we apply this vector right here, this complex number, to this reflection matrix, so reflection of 0 times our z, we're going to get, okay, 1, 0, 0, negative 1, 3, 1. Okay, if we apply this, we are going to multiply this together. We are going to get 3 up here, so 3 times 1 plus 1 times 0 is going to be 3. This together, we are going to get negative 1. And this is exactly our complex conjugate. So you see that that's actually quite a good application of this thing. You can find those standard matrices for those standard reflections, for example the line L lying on this y-axis, or for example here. But yeah, this is basically it. This is our reflection matrix and it's quite useful actually. I've seen it popping up in experimental physics, but I'm not sure anymore. I guess it had something to do with polarization, Jones matrices or something. I really don't remember, but yeah, it came up somewhere and I just derived it yesterday because it sounded interesting. And yeah, there we go. I thank you guys for watching. If you did enjoy this video, please like and subscribe and recommend channel. If you want to support channel a little bit more, you know how you can do this. And up until the next video, have a flammable day. See ya.